So the presentation is called Trust in Public Clouds and Keep Pies Away from Kids. So it has to do with two different things, something with cloud and something with Raspberry Pis, basically. Yeah, so a short outline. First, I'm gonna talk a bit about the research group that I'm leading at Westminster in London, just one slide. Then some things about cloud security with a main focus on storage, cloud storage security. And then I'm going to present an attacking tool that we built with a student of mine. So the group, basically the group was established September 2015, so it's quite new, and the group members are conducting research in cryptography, security or privacy-related protocols, and some people they are doing some stuff related to computer forensics. CSec, the group is currently a very small group. Okay, so currently we have Kami, Ayman, Dimitris, Hai Van Dang, Ali, which is a PhD, the only PhD student basically, and myself. However, we were very lucky with the projects. So during the last 1.5 years, we managed to get some significant, I would say, funding. So we have already established new collaborations, and in the next months, we are going to hire 2 more PhD students and 1 more faculty member in the level of assistant professor. So if you want a new job. So just to talk about numbers, in 1.5 years, we got 2 EU projects and 1 national project. So we received almost 1 million euros as a funding. So, but the most important thing, I mean, if you ask me what is the achievement, the main achievement of the group this almost 2 years, I would say that basically we have 2 girls in our group. No offense, but look what's going on here. I mean, it's very rare to find women in security, at least, and I'm quite happy about that. Okay, so that's all about the group. So cloud security. I'm gonna start by briefly presenting a work that I did here at SICS with two former colleagues, Nikolai Palladi and the previous head of the group, Christian German. And then I'm gonna continue presenting on how we enhance the protocol that we built here. So what we were working here is what we call a trusted computing. What is the main idea? So we have Bob, a single user. We have a CSP, a cloud service provider. And the typical scenario is that Bob basically will go and register to the CSP. Okay, so in order to use the service. And then he will generate a file. Okay, and then he will contact again the CSP, and he will basically store the file on a remote location that is occupied, that is handled by the CSP, right? Till recently, we were only thinking about, when we were thinking about malicious behaviors, about a hacker, for example, okay, we were thinking that the only attack that the hacker can do is to basically access the database, access our files, retrieve private information, and so on. So we didn't think about the CSP as a malicious entity, right? So we were thinking that, okay, the CSP says that they encrypt our data. Okay, so we rely on them. We will send the data via HTTPS. Then the CSP will encrypt the data and will store encrypted versions of our data. So we are secure. The problem is that if we consider that the CSP is malicious, okay, if the CSP is corrupted, then we need to know, okay, because we don't handle our data. Someone else, a remote location is handling, third party is handling our data. So that's where trusted computing comes into the game. So the main concept is that Bob basically will be able to verify that no malicious code is running on the remote host. So Bob should have the right tools on his hands to check if there is if the CSP is corrupted or not. So in order to do so, the CSP must be able to give certain guarantees back to Bob in order for him to verify the trustworthiness of the server. So this is done by a communication protocol between the Bob and CSP, where CSP sends basically a list of the software that was installed on the CSP and on every virtual machine that is launched on the CSP during the launch time. Upon reception of this software list, basically Bob can verify, can check if he trusts or not every software that is running on the corresponding VMs, right? So for the trusted launch protocol, we have a CSP, we have Bob, and a TTP, a trusted third party. So these are the main entities that are participating in our protocol. What is happening is that the CSP basically is launching a set of VMs, a list of VMs. And when we launch a VM, basically, then each VM generates a list of software hashes, which is like a unique fingerprint, a fingerprint of all the software that are running on the VMs. So these software hashes will be sent to the TTP, which is a party that we trust, okay? And the TTP needs to verify if the software can be trusted or not. The TTP will do that based on a certain set of security protocols that we have predefined. So an administrator, the administrator of the CSP, needs to define a set of security protocols, a set of security profiles, which means like a list of trusted software that can run on a VM. So if the list that goes to the TTP is considered as secure, then it means that the CSP can be trusted. So Bob basically gets a verification via the TTP. And the result is that the launch of VM instances are considered as trusted. So apart, yeah, well, that's an assumption that we must do. I mean, it's not. I mean, well, no, it's not. It's not the same. It's not the same because you cannot build the CSP. I mean, you go and use Amazon, right? You don't. Yeah. Anyway, but you use Dropbox. I don't know. You go and use a cloud service provider that you didn't build on your own, but you can build the TTP, for example. But anyway, in security, it's very common to rely on some protocols on the existence of a TTP. Like, for example, certificates. You trust VeriSign, don't you? But you use it. I mean, have you ever bought something online? Yeah. So yeah, yeah. Yeah, so for this, we are using the TPM. Let me continue to, yeah. So apart from the TTP, the CSP and Bob, we have some other components. So we have a TPM, which is just a hardware microprocessor, let's say, which is embedded in many devices nowadays. And it's a kind of an isolated environment. So TPM is responsible for getting certain keys, revealing information, and collaborating with the TTP in order to do what we call remote attestation. Then we have a secure component, which basically is something that we build, a piece of software, and performs confidentiality and integrity protection operations on the virtual machines. So it's responsible for doing some kind of encryption, decryption, and checking the integrity of the communication between the TTP and the CSP. And then we have the TTP, which basically communicates with the TPM in order to do what we call the remote attestation. So the TTP can verify that the TPM is trusted, okay, and then the TPM will reveal the list of hashes to the TTP. Because you can verify the certificate that you get from the TPM. You can verify the vendor, you can verify that the certificate is valid, you can verify the signature, and so on. The TPM is on the CSP, but you cannot change anything on the TPM. The TPM, yeah. Okay, so this is, I'm not gonna get into details. This is basically the protocol that we built for the trusted launch. I just want to give you the main idea. So we have a DM, which is a domain manager. You can think about it as an administrator who is giving the order to launch a VM. And this request basically will eventually go to the TTP. So the main idea of the protocol is that the DM, the administrator who wants to launch a VM, generates a unique identifier, a token, which is defined as T. So at the end, the TTP will get this request, will do a remote attestation with a TPM that relies on the that lies on the CSP, and then if everything goes okay, this token will be injected into the VM that will be launched. Okay, so the DM then will have a challenge response protocol between the launched VM and himself, and then he will verify that the VM has the token that was generated in the beginning was correctly injected into the VM. So he can be sure that the TTP verified properly, attested properly the CSP, and everything is okay. So while we were designing this protocol, then we realized that if we change a bit the protocol, or in other words, if we build a sub-protocol, we can also create something for secure storage. So what we did is that apart from doing the trusted launch, okay, we relied on the TTP to generate a new symmetric key that will be injected to the VM, will be given basically to the TPM, and the TPM will be responsible for encrypting the entire hard disk that the VM will be looking at. Okay, so basically the TTP, apart from the attestation of the data, it generates a symmetric key. Okay, and this symmetric key will be sent to the TPM. So when the VM is launched, then the TPM is responsible for encrypting the entire hard drive that the VM will be looking at, the storage resource that the VM will be looking at. So the entire hard disk will be encrypted symmetrically. So the threat model for this is, okay, we need to always have in mind our active attacker, Eve, and what we want to achieve, which is basically to frustrate Eve. So we adopted more or less the Dolev-Yao model. So we assumed that Eve can manipulate all the communications. She can replay messages, she can generate fake messages, she can resend all messages to the TTP, and she can even control a large number of networks that are not in the same place. Apart from that, we assume that we have hardware integrity. Okay, so we assume that no one can basically go physically and change something in the CSP. We assume that the TPM cannot be tampered, and we assume cryptographic security. So if Eve doesn't know the private key, she cannot decrypt anything. And if she doesn't have access to the corresponding symmetric key, she cannot decrypt the information that is encrypted with this key. So who can access my data? So in the previous protocol, we protected users' data only from external attacks. Why is that? Because an administrator can access basically the VM that has been launched, which means that he has access to the key that we used in order to encrypt the entire hard disk, right? So in other words, he can see all the data that Bob stores in the cloud. So our next challenge was to design a protocol where only data owners would be able to see the content of the data that they store online. To do so, we build a protocol based on SSC, on symmetric searchable encryption. So I don't know if you have heard about it, so it's a quite promising concept and has the potential to improve the trust that users put on cloud-based services. So with searchable encryption, users can encrypt their data with a symmetric key and can search over their encrypted data. The search has many limitations. So it's not that you can just start searching like you do on Google or on a proper database. Okay, you need, when you store an encrypted text, you need also to store a set of keywords. So otherwise, and then you can search based on certain keywords. You cannot start searching like that. So the keywords are stored as hashes. And then the key is known only to the data owner unless she shares the key with the users. Okay, so if I store my data on the CSP by using SSC, then in case I want to share this data with someone else, I need to share the key. So this is an overview of the protocol that we built. The first protocol, the trusted launch with the encryption of the hard disk, was based on OpenStack. So we built an add-on, let's say, for the OpenStack in order to have the trusted launch functionality. And then we used a platform as a service on top of that, where we built our protocol for the searchable encryption. The protocol was pretty simple. Again, we have a user who registers to a CSP, and then we have basically a distributed database, which is a bunch of different tables where we store our encrypted text that is encrypted, our encrypted file that is encrypted with a symmetric key, and then different tables that stores the keywords, the hashes of the keywords that we generate when we store our file. So every time that basically a user needs to search for a specific file, he needs to generate a keyword. Then he calculates the hash of that keyword and sends this request back to the database. So the database finds all the files that are containing these keywords, and then he sends these files back to the user, who is responsible for decrypting the files. So this approach is a bit problematic, because basically it doesn't give the option to users to share their data, or basically it makes it a bit more difficult, because Bob needs to share securely a key with another user. And the problem gets a bit harder if we think that we want to revoke access to a user after a certain time. Okay, why is that? Because if I have shared the same key with a bunch of users, okay, let's say end users, then this means that I have shared this key and if I want to revoke access to these users at some point, then it means that I need to decrypt the files, then generate a fresh key, re-encrypt the file with a fresh key, and then share the fresh key with the rest of the users, everyone apart from the malicious one, which is computationally heavy. So to overcome this difficulty, basically we came up with a protocol that is combining searchable encryption with attribute-based encryption. So attribute-based encryption allows users to encrypt data based on a policy. And each user generates a key that is bind to a certain set of attributes. So we have policies and attributes. So if a user wishes to decrypt a file, okay, the key that he owns the attributes that are bind to his key needs to meet the policy that is bind on the ciphertext. So in our scheme, we create basically the symmetric searchable encryption key in such a way that is bind to a timestamp. Okay, and what we do is that we still encrypt. The main encryption of our scheme is using SSC. So we encrypt our data by using SSC, and then we encrypt keys, the symmetric key that is used to decrypt the data, by using attribute-based encryption. So every user that wishes to access this key, he needs to use ABE, attribute-based encryption, in order to retrieve the symmetric key. So revocable key policy attribute-based encryption contains these 5 steps. I'm not going to get into details, so we just generate a master key and a public key. Then we have a key generation that generates basically a secret key, which is bind to a policy and a certain user. And then if we want to encrypt something, we need to use a public key, the message, the file that we want to encrypt, a set of attributes, and a timestamp. And then we have a function which is very important for the revocation, which is called the update key. So this function, basically, the only thing that outputs is a fresh key. So this key takes as input RL, which is a revocation list, and it's just a list with all the user's ID that have been revoked, a timestamp, and the master key. So every time that someone needs to decrypt something, okay, he needs to give as input to the decryption function, okay, his secret key, which is bind to a policy, the latest update key that he owns, okay, and the ciphertext that he wishes to decrypt. So the decryption will only work if he has a fresh key and his ID is not contained in the revocation list. If the key is not fresh, or if the key is fresh and his ID is in the revocation list, then the decryption will never work. So the protocol, the enhanced protocol with ABE doesn't change much. It's exactly the same. The only thing that we did is that we built something that we call a key tray, something like the Kerberos tray, and it's based on SGX. So we store, this place is where we store basically the attribute-based encryption version of the symmetric key that we use in order to encrypt and decrypt our files. So every time that a user wants to access some files or to search via some keywords, he first needs to get a fresh key. If he gets the fresh key and is valid and his ID is not in the revocation list, then the protocol will work. So it will work like before. So he will have to use a symmetric key in order to decrypt the data. So it was very fast, but that was about cloud computing. And now I'm going to move on to an attack tool that I built with a student of mine. So what we used is basically a Raspberry Pi, and we have many Raspberry Pis. So we have one which we call a master node, and we have installed a light version of Kali Linux on it. Then we have a bunch of other Raspberry Pis that we call them slave nodes and are controlled basically by the master node. So we were thinking of building 2 attacks, not new attacks, but existing attacks, just to see how we can implement them. So we assume that we have a user on any device, like it can be on a smartphone, on a tablet, on a laptop, and so on, who wishes to access a website like Facebook, right? So we also assume that this guy is connected to the same network as our Raspberry Pi devices. So when this guy tries to access Facebook, we intercept his request, okay? And what we do is, on the fly, we generate a cloned website of the site that this guy wishes to access. Okay, we don't clone the sites beforehand. We clone the sites on the fly, on the Raspberry Pi, and we upload them, we launch them on a local host on Apache, okay, that is running on the master node. So one requirement is that this guy, the victim, is connected to the same network, okay? Then what is going on is, instead of sending forward this request to the user, we send him back, we redirect him to our clone site, to the fake site. So this guy will see Facebook, will type in his username and password, and these credentials will be sent to the master node, which are stored on a text file, basically, that is stored on the Raspberry Pi. So the tool is still under development because we have some issues. For example, the attack was working on Facebook, was working on many websites, but it didn't work on websites that they require 2-step authentication, like banks. For example, they ask you first to give your username and then your password or something like that. So, we have an idea of how to make the attack to work, but we didn't have the time yet to finish it. We managed to successfully pass the HSTS protocol, which means that even if a website is HTTPS enabled, then the attack works properly. The only thing that it doesn't work is that if you check the bar address, you will not see a certificate. So you will see that the site is not secure, but the address doesn't change. You will see in the video next. So we have tested on Firefox, Chrome, Safari, the built-in browser of Android, and via VMs on Internet Explorer, but only on the previous versions, not at the latest version. So before I go to the video, so I asked, while I was on vacations, I asked to my student to take a recording of the attack, but he has some great antisocial skills. So even though we have a proper room at the university, he decided to make a really unprofessional video at his home on his bed. So. This is just a small monitor that we connected to the Raspberry Pi. Here, he just defines the website that we want to target, which is the e-learning platform of our university. And now he clones on the fly the website. okay, he enters the IP of the device that he wants of the victim, but now we have another function where we can scan the entire network and find the IPs of everyone. So okay, he launched the attack and now he goes back to his mobile. So this is normally an HTTPS site. You see the address doesn't change. And yeah, it's the one up at the top. No, what? Exactly. So yeah, not in that version, but in the latest version, we get the credentials and then we immediately redirect the user to the proper website that he wanted to visit. To, no, no, we don't pass the information. We don't care. I mean, there's no reason to pass the information. No. Yeah. Yeah, that's a nice. Yeah, that's a good idea. I didn't think about it. Yeah, that's a good idea. Yeah. Yeah, I guess. Yeah. I don't know now how to move. Okay. Okay, and then we started implementing a second attack, which is a kind of weird DOS attack. So usually in a DOS attack, the victim is a server, right? So with the Raspberry Pis, we cannot do any real DOS attack to a server. I mean, even if we have a farm of Raspberry Pis, it will take ages, right? So what we try to do is that, okay, we have again the same setup. So we have slave node, we have master nodes, and then we install Kali Linux with our tool, and then we scan the network. Okay, we choose a target, which is connected to the same network. And what we do is the master node sends a request to the slave nodes saying, okay, guys, this is the IP of the victim, start sending fake requests. And we just basically do a DOS attack to one single device that is connected to the same network. The result is that the device basically is, you cannot use your browser, you cannot use your phone at that point. But that's it. We didn't try to do any bigger thing. We didn't have many Raspberry Pis either. Um, so as our next step, basically, we want to implement some more attacks, and we want to try to implement the previous attack in websites that they have live content, because this is very difficult. When you try to clone a website with live content, that content changes all the time. It's really messy. Okay, so the user will immediately understand that something is going wrong. And then we want to connect, basically, we want to create some kind of a small framework how to use this attack in order to control all these Raspberry Pis remotely from a cloud, let's say, or something like that. That was it. Thank you very much.